Okay. Day 2. Here are the objectives. We're going to talk about the terms one-to-one, invertible. They have something to do with a function. And then if we restrict the domain, we can make it invertible or a function. From a table, we can make the inverse function. If we graph a function, we can also graph its inverse. And the graph and its inverse are symmetric about the line y equals x. Some of these ideas might sound familiar. And then we can be able to find the equation for an inverse. So the first idea is one-to-one. So the idea is every question has one answer and every answer has one question. In mathematical terms, every x has one y and every y has its own x. So here we go. This x value has only one y value, this x value only one y value, and so forth and so on. And so every question has an answer. That's the idea of a function. But if we go backwards, this y value only has that x, this y value only has that x, this y value this x, this y value this x, this y value this x, and this y value this x. So this is a one-to-one function. On the other hand, yes, each one of these x values has one y value, but in particular, this y value has two different x values. If I said that y is 0.1, you don't know what x value to give me. Or if I said y was, oops, that one's okay. So no, that is not one-to-one. In the graphic examples below, each of these x values have a y value. That makes it a function. And each of these y values has an x value. That makes it a function. And it's invertible. It's one-to-one. But yes, every one of these x values has its own y value. But, for example, this y value has two x values. So this is not one-to-one. Here, every x value has its own y value, makes it a function, and every y value has its own x value, so it makes it a function as well. And it's one-to-one. The idea of a machine might make sense to you in that if an x goes in, only one y goes out, not two. And if a y value goes in, notice this is upside down, backwards, only one x value comes out. Notice the orientation of these two drawings. Since this drawing is backwards, we don't call it f, we call it f inverse of x, or just f inverse. No, that does not mean reciprocal. That does not mean negative fraction. That means that the procedure is backwards. You might call it backwards f. So notice, if the inverse is above a function, it means the reverse operation. It doesn't mean make it a fraction. It does not mean reciprocal. On the other hand, if the -1 is above a number like x, then yes, it is the reciprocal 1 over x. So what the -1 is over makes a difference. Is it a function, process, or is it a number? If we give a to some function, and then we do the function backwards, I hope that it makes sense that we get a back again, so that you might say that this undoes this f value. Same thing here. If I give something to the inverse function and then I do the regular function, it gives me the same thing back. So I hope you understand that if we talk about the domain of a function, x goes to y. And if we talk about the inverse function, that was where y goes to x, the domain or starting point of the function is the same as the range of the inverse function. Vice versa, if we have the function, the range of the original function, that's the same thing as the domain of the inverse function. X becomes y, and y becomes x. Instead of x going to y, y goes to x. So if we have the original function, and if the inverse is also a function, then it's 1 to 1. 1x, 1y, 1y, 1x. And if the inverse is a function, we call that function that we started with invertible. That we can take the inverse, and the inverse is also going to be a function. And if I do that, then every x is 1y and every y is 1x. It'll pass the horizontal line test. Okay? A horizontal line, if it hits the graph twice, means that there's a y value that goes to two x values. For example, here's a horizontal line. These two x values came from the same y value. So we have a graph here. It passes the horizontal line test. If we were to switch all the x and y's, we'd get this graph, and that passes the vertical line test. This horizontal line test is the same as the vertical line test for the inverse. On the other hand, the original function here does not pass the horizontal line test, which means the inverse is not going to pass the vertical line test. So the inverse is not a function. The easiest questions we have in this section, or probably in the whole book, is taking a table and finding the inverse. And all we have to do is switch the x and y's. So here's the original table. If we switch the x and y's, we get this table. But do you see here that this y value of 1 came from two different x values? Therefore, it's not 1 to 1. So here's the inverse, and I have to restrict these two values because they share the same x values once they are the inverse. So they are inverses, or we switch x and y, and it's only an inverse function if the inverse is a function. So if I restrict or knock out the last two here, it will be made invertible. Using what we learned last time, the first difference each value increases by 4. The numbers are getting bigger and the difference is 4. So the second differences are a constant, and so the first difference is linear, the second is constant, therefore the function is quadratic, the original function. In this case, the numbers are getting bigger, so the rate of change is positive, and the difference each time is 0.3 as it gets bigger. So the first difference is a constant, therefore it is linear. If we switch the x's and y's, we get the inverse function. And if it's linear, it's also invertible. Every x is 1y, every y has 1x. If we were to find the inverse graph, take some convenient points like I have here, where they're on the grid, and then switch the x's and y's. So for example, this point is 2, 7, so I have the point 7, 2, switch the x and y. 1, 4, 4, 1, 0, 3, 3, 0, negative 1, 4, 4, negative 1, negative 2, 7, 7, negative 2. Since this example is quadratic, I need to restrict the domain. So these points here make the graph not follow the horizontal line test, which will knock out these points down here, which will make the inverse not follow the vertical line test. And so now the inverse is a function, and the original function passes the horizontal line test. So that would be from here to here and from here to here only. Same thing here. I would take these convenient points, convenient meaning they hit a grid point. And so for example, this point is negative 4, 2. So I would graph 2, negative 4. Switch the x and y. Switch the x and y. This point is 4, 4. So if I switch the x and y, I still get 4, 4. And this point is 8, 5. This point is 5, 8. And if you remember the beginning notes, it said something about being symmetric to the line y equals x. So that across this line, the two graphs are mirror images of each other. This is y equals x. For the equations, if you look at this parabola, we can see that the vertex is 0, 3. And if you remember anything about parabolas, if we go over 1 and up 1 and over 2 and up 4, that's our basic parabola, so the a value is a 1. On the other hand, and then we restrict the domain, like we said, we're going to talk about just the part to the right, and so x is greater than or equal to 0. We can say that in interval notation like this. The equation for a line, we go down 1, to the left 4, So negative 1 over negative 4. Slope is 1/4. And we can see the y-intercept is 3. That's the equation for the original. And here is the domain. We don't have to restrict it because it is invertible to start with.